Up to this point, when we've been using our undetermined coefficients method, we've only seen problems that do not have any sharing between complementary and particular solutions. However, there are times when there is a sharing of solutions between those two. So if that happens, what you're going to do is you're going to multiply by a factor of x to the nth power, where n is the smallest possible integer that eliminates duplication. All right, and I'll show you what that means in the next few examples. So basically, if the solution is repeated once, then you just go through and multiply by x squared. If it's repeated once, it would be by x, by twice by x squared. You just keep trying to multiply by a factor of x until you get to something that's unique. All right, and I'll show you what I mean once we go about through our examples. So a really basic example of this. Let's say we have the differential y double prime minus 3y prime equals or plus 2y equals e to the x plus x. All right, so yc, as we've done before, is going to be solved by the auxiliary equation m squared minus 3m plus 2 is equal to 0. And we can factor that into m minus 1, m minus 2 equals 0, and hence m1 equals 1, m2 equals 2. Nice and easy. So our complementary solution, c1 e to the x, c2 e to the 2x. Not a big deal. All right, now we're going to get a particular solution, and this is where we're going to run into difficulty, because if we were to guess a solution for this based on the right hand side, we might guess something to the effect of a e to the x plus bx plus c. But wait, notice that a e to the x, where a is some unknown value, even if it was known, would be the same as c1 e to the x. And so right there, that's a repeated solution that's shared. All right, so this is our shared solution. And so how do we take care of that? Well, instead of using a e to the x, we are going to multiply by a factor of x. So our new yp is going to be ax e to the x plus bx plus c. All right, and as you can imagine, this makes finding yp a little bit more difficult, because now we're going to need a product rule to take the successive derivatives. All right, however, it won't be all that bad. So let's get to it. Y prime of p. All right, so we're going to use our product rule. Derivative of x is 1, so we have a e to the x. Derivative of e to the x is e to the x. All right, so this is our derivative that we just got. Derivative of bx is b, derivative of c is 0. Y double prime. Derivative of a e to the x, a e to the x. Derivative of a e to the x is going to be yet another product rule. So that's going to be a e to the x plus ax e to the x. And then the derivative of b is b. So we can rewrite this by combining like terms. We have two of these ax's plus ax e to the x. All right, so now as if that isn't bad enough, now we have to sub it back into y double prime plus 3y prime plus 2y is going to be equal to e to the x plus, I think it was 3x, but just x. Okay, so that's going to become, so we have 2a e to the x. So this is going to be our 2a e to the x plus ax e to the x minus 3 of the a e to the x plus ax e to the x plus b. And then finally, plus 2 of the original solution, which was ax e to the x plus bx plus c, and that's supposed to be equal to e to the x plus x. All right, so let's have at it. Let's see what happens here. So we're going to combine like terms, and when we do combine like terms, all right, there's a piece of good news about this. All right, so we have 2a e to the x's we have negative 3a e to the x's, and so that's going to be a negative a e to the x. We have 1a e to the x, we have negative 3ax e to the x, and we have 2ax e to the x's. So this would be 3 minus 3, and so all of the ax e to the x terms are going to cancel out. And that's a good thing, because if you notice on the right hand side, there is no ax e to the x, or even an x e to the x. If that doesn't happen, to where all of those terms cancel, then you've made an algebra error and you should go back and redo it. Right? Then finally we can distribute. We took care of this, we took care of this, we took care of all the x e to the x's, so now we're going to get a minus 3b plus 2bx plus 2c, and that's going to be equal to e to the x plus x. Now we have a really nice system that we can solve. All right, so when we get down to it, we're going to have our system that negative a is going to be equal to 1, so coefficient of a equals coefficient of a. We have 2b is equal to 1. And then finally we're going to have minus 3b plus 2c is equal to 0, since there is no constant going on there. All right? And now this is a really easy solution. A is negative 1, b is 1/2. All right, so that makes things pretty easy. And then finally we can solve for c. That's going to be negative 3 times 1/2 plus 2c equals 0. We could just add 3/2 and divide by 2 on both sides, so that means that c is going to be 3/4. Right? And so our particular solution, a was negative 1, so that's going to be negative 1x e to the x plus bx, which is 1/2, plus c, which is 3/4. And finally, we can kind of juxtapose that all together to get to our final solution. So our y of x, which is equal to yc plus yp, is going to be equal to, so remember a long time ago we had c1 e to the x plus c2 e to the 2x. And then the whole reason we had to go through and get the particular solution by multiplying by a factor of x was because of this c1 e to the x. All right? And so the remaining solution is going to be minus x e to the x plus 1/2 x plus 3/4. As always, if you don't trust your solution, what you can always do is just find a couple derivatives and substitute them back into the original differential equation to see whether or not it satisfies. All right, another thing to do is just to go through and kind of just eyeball it. All right. In fact, maybe just take the particular solution and see if that makes sense by substituting back in and taking derivatives. Because usually we're pretty good with finding the complementary solution. The particular is the one that's more prone to algebra errors. All right. So if you take just the particular solution, find the first and second derivatives and substitute it, and it works, that's probably a good indicator that you're correct. Okay, so in the last two examples, we're going to see what happens when we need more than just an x as our coefficient to make the undetermined coefficients method work.